Okay, I want to talk about, we're going to get into angular velocity and linear and angular velocity. First, let's do a geometry recap. Arc length. The length of this arc we called S. Okay, make this a little bigger. Let's say my theta is 60 degrees here. Here's my arc length. Well, how do we figure out arc length? Well, based on this amount, let's say this right here. Well, it helps to know theta. In geometry, we had a formula that said the measure of an angle out of 360 times 2 pi r got us arc length. Well, 2 pi r, 2 times pi times radius is your circumference. So basically, the circumference of this entire circle, but we don't want the entire circle. We don't want the length of the entire circumference of the circle. Just this portion, 60 out of 360. Or 70 or 80, whatever theta is. So we plug in theta, 60 out of 360 times 2 pi. Let's say the radius is 6. Okay? All right? So that's basically, this right here is 1/6 times 2 pi and 6 centimeters, okay, which is the radius. And that ends up being, basically, the 6's cancel out, and you've got 2 pi centimeters is my arc length. Okay, and 2 times pi is approximately 6.28 centimeters, okay? All right, so that's how we did it in geometry. In pre-calc, we're going to make sure everything's in radians, though. So I'm going to kind of just show you again. Remember that formula from geometry where, like, we want the arc length as a certain portion of the circumference, a percentage of the angle over 360. Well, you know, 360 is essentially 2 pi. Okay, so let me kind of blow this up just a tad. Okay, so 360 and 2 pi basically just cancel out, and you're left with the measure of the angle times r. Well, we're going to change this into theta, just r times theta, r times measure of the angle, but theta has to be in radians. You remember what a radian is. 1 radian is the length of an arc that is, 1 radian is an arc length, s, that is equal to the radius. So basically r right here, okay? All right? So, arc length can be expressed not just in this old geometry formula as a proportion of the circumference. We can just say r times theta in radians gets me arc length, okay? So that's one formula I need to know. S is arc length, okay? And remember, that's like in inches, centimeters, and so forth. All right, now, let's talk about linear speed. That's the amount of arc length covered per time. Let's say you've got this object on a tire, okay, and we're going to translate it to how fast this, this spot is basically mapped out on the ground as it travels. Okay, what's its speed? How, this circumference of this tire, how fast is it laid out linearly as this point rotates around? So that's one way, this arc length. How fast is this arc length laid out on a track per time, per se? Like you follow this point here, maybe did that in a certain amount of time, okay? All right? So velocity, linear velocity is arc length per time, okay? Arc length during a given time, all right? Now let's talk about theta. Theta is going to be also, when we talk about angular velocity, is going to be how, we're going to use theta, and how fast this central angle, right, because the center of this angle is the center of the circle here, the central angle, how fast do we sweep through this? So theta is the angle that we sweep through, that we rotate through in a given amount of time, okay? So theta is the angle swept out, and we're going to divide that by t. How fast do we sweep through this angle in a given amount of time? That's angular speed. Angular speed, we're going to call that, it's kind of a funky W, it's called omega, and that's theta over time. That's k omega, all right? So we have linear speed, like tracking some object linearly, like this point, how fast is, from here to here, how fast do we make this, does this rotate around and lay down on the ground in a certain amount of time? That arc length, how much is this arc length laid out over time? How fast do we sweep through this angle over time? That's angular speed, linear speed, okay? All right, notice, let's go back to linear speed and angular speed in the relationship, okay? Linear speed is arc length over time, remember, we said that arc length was, we said another arc length was, I need my papers here, that arc length was r theta, right? R times theta, okay, was S. We did that on page 1, right here. Remember? S equals R theta, okay? All right. So I'm replacing S with R theta, but remember, what's theta over time? That's omega. So here's our final equation for linear velocity is your radius times omega, which is the amount of theta, the central angle swept through during a given time, okay? All right? Okay? And remember, omega is in radians per time, okay? Radians are unitless, okay? Radians are based on the radius. 1 radian is an arc length equal to the radius. And if this is in centimeters, this is in centimeters. So they take on the unit of the radius. Here's an example. I've got some guy here swinging a rock around or an object on a 2-foot rope in a circle, okay? We want to find the linear velocity of this object getting swung around, okay? All right, so remember, it's r times omega, and omega is theta in radians per time. Now this rock is being swept around on a 2-foot rope at 180 revolutions per minute, pretty quick, okay? Find the linear speed, velocity of the object, which is going to be r times omega. Now, revolutions per minute doesn't cut it. We need to be in theta per minute, radians per minute, okay? So we need to convert revolutions per minute. So I take 180 revolutions per minute. Remember, once around the circle, 1 revolution of a circle is 2 pi. So I'm going to convert this, 180 revolutions per minute equals 2 pi radians per revolution. 180 revolutions per minute, and I multiply it by a conversion of how many radians per revolution? 2 pi. Notice the radians the revolutions cancel out, and I'm left with radians per minute. And 180 times 2 is 360 pi. 180 times 2 pi. 360 pi radians per minute. That's omega. I still have r. Now remember, r is a 2-foot rope. So 2 feet times 360 pi radians per minute. Remember, now radians are based on this radius in feet. So I end up with 2 times 360 is 720 pi feet per minute. And I'm going to multiply out by pi and get an approximation of 2262 feet per minute of linear velocity. Okay? So the big thing is converting into theta, revolutions per minute into theta. And you just have r, and once you get, and once you get theta in radians, you can get omega in radians per time, okay? All right, we got our omega, we've got 22, we multiplied out by the pi, we've got 2262 feet per minute. What if we want miles per hour? Just another conversion. Instead of 2262 feet per minute, I multiply by what? 60 minutes in an hour, okay? And that gives me a whopping number of 135,720 feet per hour, okay? But I want to get in miles per hour, so I have one more conversion. I got it to what? I converted minutes to hours in the denominator, right? Now I have to do what? 135,720 feet per hour times 1 mile is how many feet, okay? And I convert that to 20, so it ends up being times 1 mile over 5280. So this ended up divided by this gets me approximately 25.7 miles per hour. The big thing to take away from this is what? Linear velocity is r omega. Omega is theta over time in radians per time. I converted revolutions per minute to radians per minute. And I went back and multiplied my radius times omega of 360 pi radians per minute. 720 pi feet per minute. Radians are a unitless measure. It takes on the units of the radius, which is feet. And we just did a conversion here of, here we just multiplied by pi to get an approximate. We converted feet per minute to feet per hour. And then we divided by 5280 feet per mile to get our final answer. This was just a little extra. All right. That's it, 10 minutes. Okay, that's for linear and angular velocity. All right.